What is the form for context free grammar? Context free grammar on the LHS, as in the regular grammar, we have one non-terminal, whereas at the RHS we do not have any restrictions as such. For example, one non-terminal at the LHS, and at the RHS it can be epsilon, it can be a terminal symbol, it can be a non-terminal symbol, or it can be a combination of both terminal and non-terminal symbols. So, all these rules are allowed in context free. Then which type of rules are not being allowed in context free grammars? For example, ST tends to ASB. Why it is not allowed? RHS you can have terminal and non-terminal. It is not allowed because it has two non-terminals at the LHS. Second one, you must have one non-terminal, not the terminal symbol at the LHS. And last one, you cannot have even epsilon also at the LHS. So, such type of rules are not allowed in the context free grammar. Then, why the name so? The name for these grammars, context free, makes sense because using these rules, the decision to replace a non-terminal by some other sequence is made without looking at the context in which the non-terminals occur. So, the name context free grammar. Now, let us define the context free grammar. The context free grammar G is a quadruple consisting of V, summation, R and S. What is V? V is a rule alphabet which contains both non-terminals and terminal symbols. What is summation? Summation consists of a set of terminal symbols. R, a set of rules written in the form given to the context free grammar, that is LHS one non-terminal, RHS no restriction, and S representing the start symbol. So, let us see one example of context free language. The first and foremost language which we proved that it is not regular and which is context free is L is equals to A raised to n, B raised to n, where n is greater than or equal to 0. Grammar for this language is V is equals to, you have S only one non-terminal and two terminal symbols A and B. Then summation is two terminal symbols A and B, and rule set you have two rules here, S tends to ASB and S tends to epsilon, and start symbol we have taken same symbol, that is S. So, this is how we go for defining the context free grammar as a quadruple V, summation, R and S. Next, once we write the grammar, we must go for deriving a string belonging to that particular grammar or that particular language. We say X derives Y using the grammar G. If and only if, say suppose I have X is equals to alpha A beta, and in my rule set I have A tends to gamma, then this A is replaced by gamma and this Y is equals to alpha gamma beta and X derives Y. So, starting with W0, it derives W1 string which again derives W2 and so on derives Wn, is a derivation in the grammar, and this derivation raised to star be a reflexive and transitive closure of the derivation. So, derivation will halt whenever no rules on the RHS side matches against the working string, and as we said, at any step any rule matched can be chosen. So, let us see some derivations. For the first language, the language is L is equals to A raised to n, B raised to n, where n is greater than or equal to 0. First tell me what are the possible strings in this language. If n is equals to 0, A is 0, occurrence of A is 0, occurrence of B is 0, it means the first string obtained is epsilon. Next, if n is equals to 1, then A raised to 1, B raised to 1. Next, n is equals to 2, A, B, B. n is equals to 3, A, B, B, B and so on. So, what is this language all about? It must have number of A's equal to number of B's, first thing, and second one is A's must occur first and then B's. It means B's must precede, A's must precede B's. So, how we will write the rules? So, first rule starting with S tends to, since we have the first rule as epsilon, so first rule written will be S tends to epsilon. This is rule 1. Next, I need 1A and 1B, and if you see from first string to next string, there is increase of 1A and 1B, but all A's first and then all B's. So, at that time the rule can be written as S tends to A, S, B. So, this will be rule 2. So, by this rule we satisfied 2 criteria of this language, that is first we will be having A's and then B's. One. Second one, number of A's will be equal to number of B's. Every time you call yes, it will go for incrementing 1A and 1B. Now, let us see the derivation. So, if I want to derive A and B. So, how we will go for deriving? So, you must start with the start symbol, yes, derives. So, you will apply first rule or second rule? Second rule. What it states? S derives A, S, B. Now, this A as it is, this B as it is. Now, this S, so 1A, 1B I got. Next, this S must be replaced by again applying second rule A, S, B. Now, I got second A and B. So, again what I will do? These two A's as it is, these two B's as it is. So, again I will replace S by rule 2, that is A, S, B. Now, I got all 3 A's and 3 B's. So, now it will be appropriate to apply rule 2 for rule 1 for S, that is A, S as epsilon and B. Hence, we have derived A raised to 3, B raised to 3 string which belongs to this particular language. So, these are the possible strings in the language, and the grammar written is, you can see we have used only one non-terminal, S, A and B. Terminals are A and B. Rules written are S tends to ASB and S tends to epsilon, and the start symbol is S, and possible derivations are these. And instead of writing these 4 derivations, so one more thing, you can see here 4 derivations. This can also be written as S derives for multiple instances A and B. I hope this is the simplest language. We learnt how to write the context free grammar. Now, after knowing or defining context free grammar, let us know what you mean by context free language. The language generated by the grammar, denoted by L of G is, L of G is equals to W. What is W? All possible strings which belong to summation star. What is the summation here? Summation is A comma B, such that it derives from S, it start with S and derive a string W which by using the grammar G. So, from S it will derive string A, B which belongs to language L of G. A language L is context free if and only if it is generated by some context free grammar. The context free languages are proper superset of regular languages, as we have seen in Chomsky hierarchy. So, this is the definition of context free languages. After knowing the definition of context free grammar and context free languages, let us have a quick look at the properties of context free grammar. So, first one is recursive grammar rules. What do you mean by recursive grammar rules? A grammar is recursive if and only if it contains at least one recursive rule. So, what do you mean by one recursive rule? Expanding a non-terminal according to these rules can eventually lead to a string that includes the same non-terminal again. The rule is recursive if x is equals to x tends to w1 y w2, where y derives w3 x w4, where w1 w2 w3 and w4 belong to v star. Let us look at an example, the same example, a raised to n, b raised to n. Here this rule is called recursive. Why it is recursive? Because s is recursively calling itself. So, this language or this grammar is recursive. One more example we can see, wherein s tends to t, t tends to w, and w again tends to s. So, s is indirectly recursively calling itself. So, hence these rules are called as recursive rules, and the grammar is recursive if it contains at least one recursive grammar or one recursive rule. One more example we can see, wherein we go for balancing the parenthesis. In many of the programming languages, we go for balancing the parenthesis. Let us say take a simple example of balancing the parenthesis. I will not consider all the parentheses, I will consider only one type of parenthesis. If no parenthesis means first string will be epsilon. If I have one opening parenthesis, then compulsory I must be having one closing parenthesis. If I have nested parenthesis, like nested parenthesis or in sequence parenthesis, in sequence, and so on. Now, for this we must write the grammar. So, how we will write the grammar for this? As you know, first string is epsilon, means the first rule written will be s tends to epsilon. Next, s tends to, I need one opening parenthesis and one closing parenthesis, and remember, first I must have opening parenthesis, then closing parenthesis. It is same as that of for a raised to n, b raised to n, where first a must occur, then b must occur. So, what we will do? We will write a rule, opening parenthesis, yes, closing parenthesis, which will satisfy opening and closing. And even this rule will satisfy for nested parenthesis. What if the parentheses are in sequence? So, I must have one opening closing followed by another opening closing, for which I must write one more rule, that is s tends to yes, yes. So, these are the three rules needed in order to balance the parenthesis. Shall we go for one derivation? So, we will go for sequential parenthesis. Yes, derives, yeah, for this string. In order to derive this string, which rule I must apply? I must apply yes, yes, that is apply rule 3. Now, first s will be replaced by rule 2, that is opening parenthesis, yes, closing parenthesis. Again, second s is replaced by opening parenthesis, closing parenthesis, and again s tends to epsilon, s tends to epsilon, the string is accepted, derived. So, what are the possible strings here? We have written epsilon, different possible parentheses, and the grammar is yes, opening parenthesis, closing parenthesis are the non-terminal alphabets, terminal are opening and closing. Rules, three rules, s tends to epsilon, s tends to ss, and s tends to opening parenthesis, closing parenthesis, s and closing parenthesis. And for this we have few derivations, one we have seen here. So, is this grammar recursive? Yes. Why? S is recursively calling itself, hence this grammar is also recursive. So, recursive rules make it possible for a finite grammar So, we have a finite grammar. Why finite? Because we have finite set of rules, but it generates an infinite set of strings. So, it will go for generating infinite set of strings. So, this is one property of the context free grammar. One more property is self-embedding grammar rules. What do you mean by self-embedding grammar rules? A grammar is self-embedding if and only if it contains at least one self-embedding rule. I have a rule x tends to w1, y w2, where y derives a string consisting of x, but w3 and w4 are belonging to summation plus. Then we say that this rule is self-embedding rule. For example, can I say this rule S tends to ASB as self-embedding? Yes, it is self-embedding. S recursively calling itself, and we have W3 and W4 here. So, it is self-embedding. S tends to AS, is it self-embedding? No, it is recursive, but it is not self-embedding. What about this rule S tends to AT? It is not self-embedding, but if I add one more rule to it, S tends to AT and T tends to SA, then we can say that it is self-embedding rule. So, no regular grammar can impose such a requirement on its string. Few examples of self-embedding. One more example we will take, that is W raised to R. What do you mean by W raised to R? It is nothing but a language with even length palindromes of A's and B's. What are the possible strings in this language? So, if it is star, then first string will be epsilon. Next, if W is A, then W raised to R is also A. If W is B, then W raised to R is B. If W is AA, then W raised to R is also AA. If W is AB, W raised to R is also BA, and so on. So, how to write the rules for this? So, first one is S tends to epsilon, because the first string is epsilon. Next, if you see here, the first symbol and the last symbol are the same. First symbol and the last symbol are the same. So, the rules written for this are S tends to first and last are the same symbol. So, S tends to ASA. If it does not start with A, if it starts with B, then we must write one more rule, that is S tends to BSB and S tends to epsilon. So, these are the three rules written. Derivation, yes, by applying rule 1, we will have ASA, this A and A as it is. This S applying rule 2 is replaced by BSB, and by applying rule 3 as epsilon, we will get the string AB, BA, which is a string which belongs to the language with even length palindrome of A's and B's. And why this grammar is self-embedding? Because S self-embeds with the string before and after A, or with a string before and after with a symbol B. Hence, this grammar is self-embedding grammar. So, these are the two properties of context free, that is recursive rules and self-embedding rules. Where context free grammars get their power? If a grammar is not self-embedding, then the language is what? It is regular. If the language has a property that every grammar that defines it is self-embedding, then it means what? The language is not regular. So, these are some of the properties of context free grammar. Coming to few more flexible grammar writing notations. A notation for writing practical context free grammar. A symbol, this symbol can be read as OR. It allows two or more rules to be collapsed into one. For example, you can see here, we have written three rules: S tends to epsilon, S tends to opening parenthesis, S closing parenthesis, S tends to SS. So, but our LHS is the same. Instead of writing these three rules separately, we can collapse them and write as S tends to epsilon or opening, closing S and or S, S. Both these grammars are same or equal. So, you can see here S tends to ASA, S tends to BSB and S tends to epsilon can be written by using this symbol as S tends to ASA or BSB or epsilon. This is one way. Another way wherein till now we have represented all the non-terminals by just one single symbol, whereas even we can allow a non-terminal symbol to be any sequence of characters surrounded by a angular bracket. Means, so all these characters are surrounded in an angular bracket. So, this represents one non-terminal program. Similarly, variable in an angular bracket, this represents one non-terminal. So, where we use in a Backus norm form notation for a Java fragment, you can see here LHS tends to RHS. LHS in an angular bracket represents a non-terminal, tends to opening parenthesis is a terminal symbol. Again, a statement list in angular bracket is a non-terminal, followed by a closing parenthesis flower bracket or two terminal symbols, that is opening and closing. So, if you see here block, statement list, statement, all these put in angular bracket are non-terminals, and the one in green like while, return, if, do, opening flower bracket, closing flower bracket, all these are terminal symbols. So, this is one more way of representing the non-terminal symbols. Even in a context free grammar for C++ compound statements, one more example wherein all these non-terminals are represented in angular bracket. Terminals are like if, opening parenthesis, closing parenthesis, while, do, for. So, this is one more case wherein we go for writing the non-terminals in the angular bracket. One more example, a fragment of English grammar. So, here what we do, the non-terminals are not written in angular bracket, they are written such a way that only the first character or the first symbol will be uppercase letter, rest all will be lowercase. And even we can have abbreviations like NP represents derive noun phrase, VP represents derive verb phrase. So, this is the grammar written for a English fragment where S tends to NP noun phrase, VP represents verb phrase, and if you see here nominal, nominal N represents first symbol is in uppercase. So, this is a non-terminal symbol. So, all these symbols written in orange which start with a uppercase letter and followed by lowercase letters, all these are non-terminals, and with lowercase in green the A, dogs, cat, all these are the terminal symbols. This is one more way of representing the non-terminal symbols.